Hi, welcome everyone. My name is Sid. I'm a senior solutions architect with AWS, and today we are talking about hybrid connectivity. We'll focus on AWS services which let you enable connectivity from your on-premises data centers to AWS. As an enterprise organization, you probably have a vast on-prem infrastructure footprint. This ranges from data centers to branch offices to mobile devices, remote workers, and depending upon the industry which you belong to, you might have warehouses, factories. With that in mind, you are looking to build on AWS, or you already have existing applications on AWS and you want to connect your on-premises infrastructure footprint to AWS. And you are looking for reliable, scalable, and secure connectivity to enable that. In this session, we will see how AWS can become the center of your global infrastructure footprint and enable connectivity from AWS to these different on-premises infrastructure like data centers, branch offices, as well as edge devices like your mobile applications. Let's start by talking about on-prem connectivity to your data centers. Broadly speaking, there are two options. There is AWS Site-to-Site VPN, which lets you create encrypted end-to-end tunnel between your data centers and AWS over the internet. We also have AWS Direct Connect, which lets you create dedicated fiber connectivity from your data centers to AWS. Let's focus on this option first. With AWS Direct Connect, you get consistent high throughput connectivity. You can go up to 100 gigabits per second on a single connection. If you wanted to scale the number of connections, you can provision multiple of them. That gives you high availability as well as scalability. So you can go even higher. You can bundle your Direct Connects together in link aggregation groups and load balance traffic across multiple connections. This connectivity is fully customizable, so you can control exactly how traffic is being routed, and we will talk about some scenarios in the following slides. Now, in order to establish physical connectivity from your data centers to AWS, you meet us in what we call the Direct Connect locations. These are third-party co-location facilities where AWS has presence. These Direct Connect locations are connected to the AWS Global Backbone. What basically that means is through any of our Direct Connect locations, you get access to all of AWS's global footprint. So you can have your Direct Connect locations in core site New York, and you can access AWS services in, let's say, the Singapore region. Note that AWS China region is not connected to this global backbone. Within this Direct Connect locations, we have what we call the AWS Direct Connect devices in AWS own cages. Now, you will establish connectivity from your data centers to these Direct Connect locations. You can host your routers in cages in these co-location facilities. And if you don't have this presence, you can reach out to any of AWS's networking partners or your own ISP and request connectivity. Finally, you go to the AWS console, request a Direct Connect connection. We will allocate a Direct Connect port in one of our devices, give you a letter of authorization, which you can then take to the vendor to establish the last mile final cross connect. Once you do that, your physical connectivity is completed. Now, in the sample setup here, we have two Direct Connect locations and two connections. In reality, you would probably want to create even more connections for higher availability. We have the Direct Connect Resiliency Toolkit, which lets you determine exactly how many connections you need, and it also goes ahead and places the order for those connections, really simplifying the process. Now, once the physical connectivity is done, let's see how you can get access to AWS resources. So for that, let's bring in a sample AWS network infrastructure setup. Here we have two AWS regions. You have US East 1 and US West 2. We have two VPCs in US East 1 and one VPC in US West 2. And we want to establish connectivity from your on-premises to these VPCs. Let's see how do we do that. Number one, you create what's called the AWS Direct Connect Gateway. It's a global, dedicated, isolated router. It lives in your AWS account, so it's dedicated to you. It's highly available and it's a logical entity. Next, you connect your VPCs to the Direct Connect Gateway. Now, for your routers to get access to Direct Connect Gateway, you need to create what's called a private VIF. And while creating the private VIF, you have to specify a bunch of BGP parameters, peer IP addresses, BGP authentication password, ASN numbers, and as well as a VLAN tag you want to use to tag your traffic. Once you do all of that, AWS Direct Connect Gateway gets auto-configured, and you get a configuration file which you can download and use to configure your end of the connection. Once you do all of that, a BGP session gets established, and the Direct Connect Gateway will learn all of the IP addresses of the VPCs and advertise it downstream to your router. And you can advertise IP prefixes from your end as well to Direct Connect Gateway. Direct Connect Gateway is going to learn those prefixes which you advertise and propagate it downstream into the VPC subnets. Now, you might have an alternative network architecture in AWS where you're leveraging AWS Transit Gateway. Now, if you're doing that and you want connectivity from on-prem to these transit gateways, the process is very similar. You create the AWS Direct Connect Gateway. You attach the transit gateways to Direct Connect Gateway, and you create what's called the transit VIF. Configuration-wise, transit VIF is very similar to private VIF, and you establish a BGP peering relationship between your router and the Direct Connect Gateway. Now, one fundamental difference in this setup is on Transit Gateway, you control exactly what prefixes you want to advertise downstream, and that's a static configuration. So as you can see in this example, what we're doing is instead of advertising each and every VPC CIDR range, we are summarizing it at the Transit Gateway level. Right? This gives you a nice advantage of keeping things simple and not advertising like a whole range of IP ranges and just summarizing them and keeping them manageable. Direct Connect Gateway learns these IP ranges and advertises it downstream to your routers. And as we talked previously, you can advertise your ranges to AWS Direct Connect Gateway, and AWS Direct Connect Gateway is going to propagate those IP ranges in the Transit Gateway route tables. Perfect. Let's recap. So we talked about how you can use private VIF. Now keep in mind that with private VIF, a Direct Connect Gateway can connect to up to 10 VPCs. With Transit VIF, a Direct Connect Gateway can connect up to 3 transit gateways. And over each connection, you can advertise 20 prefixes from the Transit Gateway to the Direct Connect Gateway. Finally, there's a third kind of a VIF. We didn't really talk about that in the previous slides. It's called the public VIF. The fundamental difference between private VIF and transit VIF versus public VIF is that with private and transit, you get access to VPCs. And with public VIF, you get access to the Amazon's public IP ranges, right? So these are services like Amazon S3, DynamoDB, the management console, which are backed by public IP ranges. Now, broadly speaking, there are 2 different connection types. We have dedicated connections. And when you're using a dedicated connection from 1, 10, or 100 gigabits per second connection speeds, you can provision 50 VIFs and 1 transit VIF. So those 50 VIFs can be 49 private VIFs and 1 public VIF. And in addition, you can provision 1 transit VIF. There's a second type of connection, which is called the hosted connection, where you can go even lower than 1 gig. Sub 1 gigabits per second up to as low as 50 megabits per second. In order to get a connection like this, you need to work with an AWS Direct Connect partner. When you do that, you can provision only 1 VIF, right? So it can be a public VIF, a private VIF, or a transit VIF. And transit VIF is only allowed for 1 gigabits per second and up. Great. Now we know how to establish Direct Connect physical infrastructure, and we also know how to establish the logical connectivity to get access to your VPCs and transit gateways. Now let's focus a bit on routing and how it works. So I have a sample setup here where in VPC in US East 1, a packet is being originated with a destination IP address of 192.168.1.34. Your on-premises data centers are advertising 192.168.0.0/16 summary route from both the connections from both the Direct Connect locations. So this traffic is sent to Transit Gateway, and Transit Gateway sends it off to Direct Connect Gateway. Now, Direct Connect Gateway sees two paths. It sees a path through core site NY, and it sees a path via tier point in Seattle. Which location and which circuit does it choose to send the traffic downstream? Let's see how it plays out. So the traffic goes through the core site NY location. Interesting. Let's see another scenario where the traffic is now originating from the VPC in US West 2. Exactly the same destination site range. The traffic goes to Transit Gateway, to Direct Connect Gateway, and then from there, it chooses tier point Seattle. There's a pattern here. And in order to understand that, I want to show you this screenshot from the AWS documentation. As you can see, there's a Direct Connect location and an associated AWS region. So the routing logic is, if the traffic is originating from an AWS region, we will always prefer the associated Direct Connect location. So when the traffic originated from US East Virginia, it preferred the core site New York Direct Connect location because that's associated with the region and that's the preferred way. Similarly, when the traffic originated from US West Oregon, it preferred tier point Seattle because that's the associated region, right? This is great because you want low latency. So when the traffic is originating from one part of the continent, the traffic should flow downstream through a Direct Connect location which is close to it, right? And that's the logic which we apply here. The Direct Connect location, which is nearest to the region, is always preferred. Now let's change the scenario a bit. Now in core site NY Direct Connect location, we add another connection, right? So we have two connections in core site NY. You're still advertising the same summarized prefix from all the locations and all the connections. The traffic is sent to Direct Connect Gateway. Now Direct Connect Gateway needs to make a decision. We know that if the traffic is originating from US East 1, it's going to prefer the core site NY location. We just learned that. But within core site NY, which connection does it choose? Let's have it play out. So it chooses the lower connection, the light green connection. Let's try again. In this case, it chooses the other connection. Is there a pattern here? There isn't. When traffic is being sent to a Direct Connect location, if there are multiple connections within a location, AWS Direct Connect Gateway is just going to load balance the traffic, right? Which might be great for you because you get active-active kind of a setup, built-in high availability, and you can scale as your demand grows. Or if you're using a firewall at your end, which which captures packets and states and stuff, you probably don't want active-active setup and want to avoid any kind of asymmetric routing. So what you can do is you can use AS path prepending. What we do here is when you're advertising the routes to AWS, you can tag them with additional AS numbers. By doing this, you are making one path shorter and other path longer. So we can see here that the lighter green path is a longer path because there are two AS numbers associated, versus the dark green topmost connection is a shorter path because it just has one tag. So next, when we send the traffic, it's going to always prefer the topmost path. And it'll be consistent. You can send multiple packets and you're seeing every time the package just keeps preferring the topmost connection. Now, if that goes down, yes, it will fall back and use the light green connection. And if the entire location goes down, then it's going to start sending traffic via tier point Seattle, right? So this is what I call most optimal routing, lowest latency, but it's using high availability of AWS Direct Connect infrastructure as well. And this is something what you should be architecting for when building production workloads in AWS. If you want to learn more about how BGP routing works, some of the additional configuration options you have, I have a QR code on the top right. Just scan it. It'll take you directly to the documentation where you can learn more. Perfect. We saw how Direct Connect works. Now let's jump into the next option, AWS Site-to-Site VPN. With AWS Site-to-Site VPN, it's over the internet, creates a IPsec encrypted tunnel. On the AWS end, you get a fully managed endpoint, so you don't need to create any custom configurations or host your own appliance, nothing like that. It's fully managed. It's highly durable. We give you endpoints in multiple AZs, and we'll see in the next slide how it looks. It's horizontally scalable. We have ECMP support, where you can load balance traffic across multiple VPN tunnels to get greater bandwidth. Something which is new is now AWS can initiate IKE negotiation, right? This was not supported until very recently. You get the latest crypto, AES 256, SHA algorithms. You have an option of using pre-shared keys for your secrets or even certificates. From a routing standpoint, we support BGP dynamic routing, or you can also configure static routing over these VPN tunnels. Finally, we also support NAT traversal. So let's look at how this works. So we have data centers on the right. We have an AWS infrastructure on the left. You create managed VPN connection on the Transit Gateway. When you do that, you get 2 IP addresses. These IP addresses are highly available and redundant and map to different availability zones. You go ahead and create VPN tunnels. One IPsec VPN connection is 2 VPN tunnels, right? So for every time you're creating a VPN connection, we recommend that you create 2 tunnels because that's how you get high availability. You get 1.25 gigabits per second per VPN tunnel. But on Transit Gateway, we support ECMP. So if you want higher bandwidth, you can go ahead and create additional IPsec VPN connections, get more tunnels, and then load balance traffic across these tunnels using BGP. In this example, we have 4 tunnels. So 4 into 1.25, got my maths right. That's 5 gigabits per second of VPN throughput right there. Now, if you wanted to set up an active standby, you can use some of the mechanisms which we spoke previously, like AS path prepends or MED metrics to convert your links into active standby. Now, if you are connecting to the VPCs directly through the virtual private gateway, you can still create IPsec VPN connections. You still get 2 highly redundant endpoints to create connections to. But the only difference is that you don't get ECMP, right? So your tunnels are in active standby by default. Also, you'll need to create an IPsec connection to each and every VPC if you're connected to it directly. So Transit Gateway makes a lot more sense because we create connection to Transit Gateway once and you get access to all the hundreds or thousands of VPCs which are sitting behind Transit Gateway. And in addition, you also get better functionality like ECMP and accelerated site-to-site VPN, which we're going to talk about next. So when you create site-to-site VPN, it's over the internet, right? And let's say your data center is in New Jersey and you're trying to access the Transit Gateway over VPN, which is in US West. Forget US West. Think about connecting to a different continent like Europe or Singapore. Your packet is going to flow through multiple networks, your local ISP, and then multiple networks right in there. You don't know which networks, how many networks. There can be congestion. There can be packet loss, jitter. Needless to say, you're not going to get the best performance and latency, right? But we can solve that. Using accelerated site-to-site VPN, you have an option of sending traffic into the AWS global infrastructure as soon as possible via our edge locations. So when you're using accelerated site-to-site VPN, in this example, the IPsec VPN traffic can be sent from your data centers in New Jersey to the Newark, New Jersey edge location, which is Amazon's edge location, AWS edge location. And from there, all the way to the remote AWS region, in this case, US West 2, the traffic is sent over Amazon AWS backbone. This is completely congestion-free, so you don't have to worry about the uncertainties of the internet, right? And you can just send traffic via local ISP to AWS and then all the way to the backend region. For this infrastructure, for this service, we use what's called the Global Accelerator, and we'll talk about Global Accelerator towards the end of this presentation. But that service has 96 points of presence in 84 cities across 46 countries, right? So rest assured, you can get congestion-free, optimized path from your data center to any AWS region using accelerated site-to-site VPN. Perfect. Now, we saw how connectivity can be established to direct to your data centers. Now, let's jump into branch offices and remote users. Let's start by talking about branch offices. The unique thing about branch offices is there are a larger number. Right? Every enterprise organization has strategically placed branch offices in different cities across the globe. New York, Seattle, London, Singapore, India, Mumbai, Bangalore, you name it, right? 50, 100, even thousands of branch offices. Right? Now, you can still use AWS Site-to-Site VPN, create a IPsec VPN from these branch offices to AWS. Or if you have an MPLS setup already connecting your branch offices, you can use Direct Connect dedicated connectivity to bridge your MPLS to AWS. That's a completely valid option. But I do want to talk about a third option. I want to talk about using SD-WAN. SD-WAN is gaining a lot of popularity in the recent times, and for the right reasons. It gives you the agility and the flexibility of spinning up WAN connectivity in a very fast manner. It has reduced costs. It gives you more visibility. And that is possible to achieve in AWS with Transit Gateway Connect. Transit Gateway Connect is a new service, a new feature which we released, which lets you connect your AWS infrastructure to an SD-WAN appliance. We have direct native integrations with 12 plus AWS partners. Again, if you want to learn which vendors and partners Transit Gateway has native integration with, scan this QR code. It's going to take you directly to the list of the partners and more information on how that integration works. Very high level, this is how it works. You have AWS infrastructure on the left. You have your branch offices on the right. Now it's time to connect them together. Number one, we create an SD-WAN VPC. It's just a regular VPC where you host your SD-WAN appliance on EC2 instances. This is one of those 12 partner appliances which we have integrations with. Now, I just have a single appliance here, but for high availability, I recommend multiple appliances in multiple availability zones. You create your SD-WAN connectivity to this appliance. Now, in order to bridge the SD-WAN infrastructure on the right to the AWS infrastructure, number one, you attach this SD-WAN VPC to Transit Gateway. And next, you create what's called a Transit Gateway Connect attachment. This lets you create a GRE tunnel between your SD-WAN appliance and Transit Gateway and establishes a BGP peering within this tunnel. Now, over this Transit Gateway Connect attachment, your SD-WAN appliance can speak directly to Transit Gateway, exchange all the routes, and perform health checks, know the link is up and running, and you get great bandwidth. You get up to 5 gigabits per second per TGW Connect attachment. Now let's jump to remote users. Now we are all living in a world where remote working is a default. So getting remote users access to AWS environment is pretty key. So here we're going to talk about an AWS service called AWS Client VPN, which lets users connect to AWS from their laptops and desktop devices. And they do that with the help of a client. So we'll be referring the Open VPN client. Now, AWS Client VPN also offers clients for Windows, Linux, and Mac devices. So you can use that, or you can use any Open VPN client. Let's see how this connectivity works. So again, we have AWS infrastructure on the left. We first create a client VPN VPC. Again, just a regular VPC, but within this VPC, we'll provision the AWS Client VPN endpoint. Now, the users using the Open VPN client will authenticate with this AWS Client VPN endpoint. Now you can use Active Directory credentials, you can use SAML federation, or you can use certificates for authentication. But once the authentication is complete, the user is authenticated, they will get access to the client VPC. Now, if you want the remote users to have access to rest of the AWS infrastructure, very simple. You just connect the Transit Gateway to this client VPC, and by design, users will get access to any network which is connected to the client VPN VPC. Now, in not all cases would you want that users are getting access to all of your AWS infrastructure. You want to restrict users into specific VPCs. Let's say you want your remote users to access only the development VPCs and not have access to the prod VPCs. You can do that. There's an authorization component to Client VPN where you can write authorization rules which restrict access to networks. Perfect. Now let's talk about our final connectivity option. And this is for your edge devices. Right? These can be smart cars, these can be smart factories, these can be mobile devices with your applications in there. And we're going to talk about a new service, AWS Global Accelerator. Now, in order to connect your edge devices, you can still use VPN, you can still use SD-WAN. This is a service in addition to some of the previously mentioned AWS services. Now, the unique thing about edge devices is that they should get low latency access, a congestion-free access to your infrastructure in AWS. And the other thing is the edge devices can be mobile, right? They can be moving. You might have a user with a mobile application and he's in US one moment, and after a few days he travels, he goes to Europe, or he might be traveling to India, and his mobile and keeps moving. What you want to do is give him the best performance possible. The same with something like a smart car, right? It keeps moving. So what you can do is, using Global Accelerator, route traffic from your edge devices to the nearest edge location, and then use AWS Global Backbone to send the traffic downstream to your application stack, which is, in this case, in our example, backend is the application load balancer, front-ending an auto-scaling group of EC2 instances. Now, let's see how this works with an example. So let's say you have your application stack in India, Europe, and United States. And then you have your edge users, smart cars, factories, mobile apps distributed across different parts of the globe. You create a global accelerator, right? You give it a name. Let's call it SID App 1. You need to define a UDP listener port. This is the listener port at which your global application listens. So it's 7453, just a random port. Next, you need to define what your backend is. So I have 3 backends here. I have endpoint group 1, endpoint group 2, endpoint group 3. I add all of the 3 endpoints to my global accelerator. Here, I'm adding the application load balancer within those regions as my backend. Finally, when you create the global accelerator, you get 2 Anycast IP addresses. These Anycast IP addresses are advertised from all of the Amazon's edge locations. So when a user tries to access these IP addresses, they are routed automatically to the nearest edge location. And from there, they are routed to the nearest AWS region over the AWS backbone. Now, there's a lot more functionality here. AWS Global Accelerator is also performing health checks. So let's say your endpoint group 2 has a failure, or that region has a problem, right? Global Accelerator will detect it and automatically reroute traffic to endpoint group 3, which is the nearest region from that edge location. Additionally, let's say you bring up a new version of your application, right? You add more functionality. It's called V2. It's great, nice. You want to roll it out. But you don't want to roll out globally everywhere. You want to have a step-by-step rollout. So you can use waits to route specific traffic to the new application stack. And if, let's say, you're doing a blue-green deployment, you can actually completely shift traffic to the new stack, right? So this gives you a lot of flexibility in how the traffic is being sent between different endpoint groups. Perfect. So in today's presentation, we saw how you can keep AWS at the center of your global infrastructure, use Site-to-Site VPN over the internet, and AWS Direct Connect's dedicated fiber connectivity to connect your data centers to AWS. We also saw how you can connect via AWS Client VPN and SD-WAN connectivity to branch offices and remote users. And finally, we saw how you can connect your edge devices, smart cars, mobile devices, smart factories using Global Accelerator and give them the lowest latency possible as well as high availability. If you want to learn more, I definitely recommend check out AWS Training and Certification. We have a bunch of different free digital courses. You can learn more about Transit Gateway and deploying VPCs. And once you learn all of those fun stuff, definitely try to appear for the AWS Advanced Networking Specialty Certification. Thank you very much. I hope you enjoyed today's session. Please complete the session survey. Your feedback is very valuable to us. We look at it very diligently and act upon it. So I hope you complete the session survey and provide us some valuable feedback. Thank you very much.